Hello, we are Team Supfina, and our focus is on data collecting using IoT systems, which are Industrial Internet of Things. Our technical directors are Mason Dumaine, who graduated from URI in 2019 and is an electrical engineer, and James Lospoluto, who also graduated from URI, class of 2010. Meet the team. We have Natalie Cruz, who is electrical engineer. My name is Aaron Linares, I'm an electrical engineer. James Yang, who's a computer engineer. And Hong Sen Tran, who's also a computer engineer. A little bit about Supfina. They are one of the largest suppliers of abrasive finishing machines and attachments. And the sister company, which is Supfina Gracehabe in Germany. And their focus is on automotive parts and bearings. Moving forward to implement developing technologies. And the motivation for this project was to integrate a comprehensive IoT system able to collect data from the sensors on the machine implemented. This will help meet the customer demand, which is less downtime, faster, smarter machines, transparency, and reduce the human labor by tracking if anything goes wrong in the machines or something is going to break down or isn't working properly. Now I'll be passing it on to Natalie Cruz.
Thank you, Aaron. Our anticipated best outcome was the implementation of a hardware and software-based data collection system that would allow Supfina to monitor products remotely from anywhere in the world and address issues before they arise. This would help minimize downtime and reduce thousands of dollars of travel and maintenance costs every year. Developing this system would allow Supfina to showcase their features and offer packages to new and existing customers for manufacturing processes. The savings would then transform into revenue to focus more on growing technologies. Although the anticipated best outcome was not fully achieved, we did research and select sensors for data collection. We updated the schematics, and we started integrating and configuring the sensors to the machine. We also created a web server for a user interface that was capable of receiving and displaying data. On the left, we have the IO-Link master, which connects to the IO-Link capable sensors. And on the right, we have the inside view of the electrical cabin where the analog output power meter is located. As you can see, the IO-Link is capable of communicating multiple signals over one channel, unlike the analog counterpart, which requires more connections. IO-Link reduces the complexity of related circuits and connections. On the left is the AccuVim2 power meter mounted on the exterior of the electrical cabin. On the right, we have the flow sensor in line, measuring the compressed air that goes to the machine. This is one of the schematic pages that were updated, which shows the IO-Link master and the connections to the IO-Link capable sensors. Aaron will go into further detail as to what other changes were made. Team technical accomplishments include the analysis of industrial Internet of Things systems and communication protocols, the research and selection of industrial automation sensors, the consultation with outside company sales representatives, the preliminary hardware design, the learning of fundamentals of software tools and web development, finalizing the wireframe for the website, updating machine schematics with the new sensors and implementing the sensors onto the machines, programming scripts to process machine data, and creating the website for user interface. The economic impact of this project is that it will elevate Supfina Machine Company above its competitors. This project has the potential to draw more positive attention and clients to the company, which would create more business and sales. The possibility of more profit would allow Supfina to further expand their research and explore new areas within the industry, as well as ultimately cutting back the cost of travel and downtime for the companies using these machines. The ability to monitor and repair a machine remotely allows Supfina to provide more customers with exceptional service. The system block diagram shows the flow sensor, the air meter sensor, and the condition monitoring sensor connected to the IO-Link master, which use IO-Link communication. The IO-Link master is then connected to the programmable logic controller, or PLC for short, which use Ethernet IP communication. The power meter connects to an input-output module to be able to connect to the PLC, which uses analog communication. The PLC is then connected to the E1 Flexi modem using Ethernet IP. The modem sends the collected data to the Amazon web server through Wi-Fi. The user interface also connects to the web server through Wi-Fi to receive the data that it will display to the user. My individual technical contributions include the research of communication protocols such as IO-Link and Ethernet IP, the research and selection of sensors such as the airflow rate, the vibration and velocity, power meter sensors, and temperature and humidity sensors. I also consulted with sales representatives and engineers to choose the correct sensors. I helped plan the connections needed between sensors and the PLC. I also helped add the sensors to the schematics on the ePlan software. I helped with the hardware implementation and physical connections of the sensors onto the machines. Now, Aaron Linares will go into further details with regards to his individual technical contributions.
So my individual technical contribution, I did research into IO-Link, Ethernet, or the different communication protocols, and then analog digital, which were the main ones we used on our machines to track the data. And then from there, select the sensors needed to find airflow rate, vibration velocity, power meter, and a sensor to measure temperature humidity. Once all the sensors were selected, I also worked on the schematics for ePlan and updating those for the Spyro and Nano and implementing the new sensors. I also worked on the wiring for the PLC, E1, and all the sensors and how they would communicate to then effectively send all the data to the web server, as well as work on updating the schematics on ePlan for the Nano and the Spyro, adding in the new sensors, the wiring, as well as adding to the PLC and E1. And that was all done through looking through other machine schematics and seeing how they wired things up and really learning how everything was laid out, and then looking at the specific schematics that already had an IO-Link master, and from there rewiring and renaming certain parts with the new components. Once that was done, then assisted with implementing and wiring the sensors into the machine, so mainly the Nano, just because we didn't have time to get to the Spyro. And it was pretty cool seeing how everything was direct translation, so looking at the schematics and then applying that to the physical hardware from the machine. So here we have the schematic of the page where we have the IO-Link master switch and where that gets its power, and then how the sensors are then connected to it on the right side. So these sensors have the positive, common, ground, and the communication. And then here we have pictures of the IO-Link master, which is installed, so that we have the cable where then it connects to Ethernet, connecting to the PLC, and below that, so that's the green wire, and then below that we have the power cable. And then on the right we have the power meter, which is installed on the panel to the side, and how that is receiving power, measuring the current through current transformers connected directly to the wires on the 480 voltage coming into the machine. We worked on configuring mainly the power meter, just because we realized that the power wasn't high enough for how it was stock. So we found that we needed to add more current transformers to then add to the scaling and make that more accurate. And then connecting that to the PLC. And then we have the flow sensor, which was installed through the pipe where the airflow goes into the machine. I'll be passing it down to Hung Sun Tran.
Hello, my name is Hung Sun Tran, and I'll be talking about the user interface portion of the project involving web development. In order for this to be done, Jason and I needed to be proficient with HTML and JavaScript. HTML is what comprises what you see on websites. When a web browser reads HTML, it looks at the tags given in the program, like a head or a body tag. These tags gives information to the browser of how the information should be displayed, and it provides meaning to the text. We also needed to learn CSS. CSS means cascading style sheets, and that is used for web design. It is what gives color and text format to the words that you see on websites. Some Bootstrap libraries were used to create the sidebar and navigation bar. The sidebar provides access to the company's contact information or support for whenever the consumer needs assistance or has questions. JavaScript is what makes the web browser interactive. For this project, we use JavaScript to create a table and a graph, which will be shown in the next slide. The JavaScript you see on the side was used for the graph, as I said. It takes data given from a JSON file and displays them. Here we can see the graph that was created using old machine data. The data was pulled from an AWS database and was formatted into a JSON file that was used in a script that we created in Java. We also tested the connectivity of the AWS database. Jason will now talk to you more about AWS and DynamoDB.
Hello, my name is Jason Yang, computer engineering. I will be discussing details about the integration of our website, specifically how we would integrate our data and display it on the web page that we developed. So our primary objective for the past semester was getting our website to load and display data from Amazon Web Services. First, I'll talk about the website, which is integrated according to the wireframe we created last semester. It's fully responsive for mobile devices if mobile development is in the future of this project. Hungsen and I were in charge of researching the tools to build the site, including HTML, CSS, JavaScript, file management as far as web development is concerned. And we were in charge of coding it as well. In order to display machine data on the front end, our computer engineering team used the DynamoDB test program in Eclipse to send data to a JSON file, which would then be converted to a graph on our website. While these results were simulated, as you can see in the bottom right corner, they provided a good foundation for what the finished project would end up looking like. Our website was built so that additional tabs could be used to display a variety of machine parameters that our electrical engineers would install sensors for. For our sample program, we just stuck with pressure, temperature, and power consumption. However, a simple line or two of HTML would add more tabs to take a look at different parameters. In the future, we hope that the link between AWS is established so that our actual data can be displayed. While our anticipated best outcome was not achieved, our team has a good idea of what steps need to be taken to finish this project. This includes the programming of the E1 and the PLC. There's some debugging and testing that needs to be done, and some additional features that would make the project more manageable in the future. Our logbooks and documentation that we wrote up for this semester should make the steps forward fairly simple for future engineers. And as our capstone program draws to a close, we would like to thank Dr. Harris Sunak, electrical engineer Mason Dumaine, and our consulting technical director Jeremy Peacock for their continued support throughout the program. Our team would not have been able to learn as much as we have without their help and feedback. On behalf of the Supfina team, thank you.